All right, welcome to Math 331. I believe this is lecture 20. Yes. And so we're going to continue our discussions of how long, how many. The idea today is to really get into using memoryless processes as well as writing code. I'm excited to see some people in the audience who know how to code well, who will hopefully be able to find mistakes as I make them. I somewhat cheated by writing the really basic outlines of the code just to start doing the loops and printing things out, but not any of the actual algorithms. So hopefully you can have good input from me on how to do this well. All right, so the problem we're looking at is in Bridge, the 52 cards are dealt 13 to a player, so there's 4 players, and so the 52 cards are split. So each hand, each deal, you get 13 cards. And then you take the cards back, you mix them, we'll assume it's a perfect mix, and each hand is as likely as any other to be dealt to you. How many deals do you need on average before a player has seen every card? Once we solve this, we can do the more challenging problem. How many deals do you need before everyone at the table has seen every card? Let's just focus on one person. I can give you a trivial bound. I can be really stupid, or I can be moderately stupid. I'll do moderately stupid. How many new cards do I see on my first hand? 13. So I know really after the first hand, I only need to see 39 more. I will, without loss of generality, I might as well assume I got all the spades on my first try. I can normalize it that way. So I need to get all the hearts, all the diamonds, all the clubs. I will focus on getting, the cards one at a time. And even though I'm dealt 13 cards, I'll only look at the first card that I'm dealt. So I can use the old prize problem and get a really bad upper bound. This is incredibly wasteful, but at least I have some rough sense of how bad it's going to be. Okay, let's do a little bit better. Normally, a deck of cards, and this is the amount I was able to find in my backpack. I do have a better deck than this. I don't know where the rest of them have gone. Has 4 suits. Each suit has the numbers either deuce through ace, ace through king, however you want to do it. There's 13 cards. We can consider the more general situation where we have 4 suits. Oops. So we have 4 suits, and we have maybe C cards per suit. What's the easiest case of C to solve? Easiest case of C. 1, right? If there's only 4 cards, so we have, say, ace of spades, ace of hearts, ace of diamonds, ace of clubs. And when we look at it, you get 1 card. So how long do we expect to wait? Well, we've got 4 prizes. We get 1 each time. This is the classic prize problem. So classic prize problem if C equals 1, right? And so the wait should equal 4 times 1 plus 1/2 plus 1/3 plus 1/4, or 4H4. Everyone agree this is not that challenging, this is not that exciting. Right. It's obvious, but I have to ask it. What C should we look at next? 2, right? This part of the lecture is kind of boring. Okay, C equals 2. So now it's a little bit more interesting. So now there's 8 cards. Let's say ace, deuce of spades, ace, deuce of hearts, ace, deuce of diamonds, and ace, deuce of clubs. Without loss of generality, we get the ace and deuce of spades on the first deal. So now we have 6 cards left, but we get 2 at a time, right? So 6 cards left, get 2 at a time. So what are the possibilities? Excuse me, could you please take off your hat? Yeah. If it was a different hat, that would be fine, but that hat, yeah.
Are you rooting for the Dodgers this time?
I'm rooting for the media strike. They had a nice image as to who's rooting for which team. And so Massachusetts is rooting for the Dodgers. Southern California is rooting for the Yankees. I think Florida is also rooting for the Yankees, and then the rest of the country they have rooting for media strike. So there's 6 cards left. What are the possibilities on the next deal? So what could happen on the next deal? I could get the same cards again, in which case, in some sense, for the analysis, it's actually good, because that's like nothing happened, and we just increment the wait time by 1. What else could happen? I could get one of the new cards, or I could get 0 of the new cards, or
a different one of the cards.
So I could get 0 new cards, 1 new card.
Sorry, 2 new cards.
Or 2 new cards.
Yeah,
so I've got 3 possibilities. So we want to figure out what's a good variable. Indices are good. Sometimes we use colons to indicate some of the parameters that don't really change. So let's let W be the wait time. This is going to be maybe the number of cards that I have. Or do I want to do the number of cards I have or the number of cards that I need? Maybe need. So need, and I'll put a colon and maybe the total number of cards. So this is going to be the wait time if need n more cards and there are number of cards total. So as we're playing this, is the number of cards going to change? No. And so this way, I'm trying to do things in a little bit more generality so that when I write the computer program, I don't want to hardwire in something like 52. That needlessly limits me in terms of what I can do. I want to keep that as a free parameter. N is going to be the number of cards I need. Should I keep track of the number of cards that I have? Is it worth having an index for that?
You just got to find it.
Right, we know the number of cards, we know how many we need. Okay, now if you use that argument, if you look at standings in baseball, they give you the number of wins, the number of losses, and the winning percentage. Do you need the winning percentage? No, but you don't really want to see Americans do division, right? And it's nice to just have it, it's convenient to have it. You could put in another parameter just to make things a little bit easier to see, but I'm not going to waste space like this. So let's take the situation where the number of cards equals 8. After one try, we know we have 6 more to go. So if I want to calculate how long do I need, I start off, I'm missing 8 cards out of 8. And after one turn, I know I'm going to get 2. And then I'm going to have 6 missing out of 8. How would you calculate the wait time for 6 missing out of 8? So what are the things that you, yes?
Wouldn't it be probabilistic with like
It would, yes.
plus some probability of W4, comma 8, some probability of W5,
Yep.
and some probability of W6.
Now, so W68, what are the 3 states it can go to?
6, 5, 4.
So it can go to W 48, W58, and W68. What's the probability it goes to W68?
We dealt the same pair,
You dealt the same pair.
and that's 2 out of 8.
We got to be very careful. We're choosing 2 cards out of 8. How many ways did it choose 2 cards out of 8? 8 choose 2. And how many ways did it get the same pair of cards as before? There's just one way.
Yeah.
So this would just be 1 divided by 8 choose 2. What about how many ways are there to get 1 new card? We first have to choose a card that we already have. How many ways are there to do that? 2 to choose 1. And now we have to choose a card that we don't have. How many ways are there to do that? That's just 6 choose 1, right? And then we would divide that by 8 choose 2. And now, how about W48? We need to choose 2 cards we don't have. How many ways can you choose 2 cards that you don't have? Six choose 2. And we divide that by 8 choose 2. And then we keep going down like this. And so now, do we have to worry about continuing with that branch? Yeah, just recursive. So that's going to just come back. So we don't have to worry about that, which is good. And then the 5 choose 8, where can that bring us to?
3, 4.
3, 4, and 5. So it actually could bring us to the 4 choose 8. So one possibility is it's going to go to the 4 choose 8. One possibility is it's going to loop back to itself. And then another possibility is it can go to W3 choose 8. And then the 4 choose 8 could loop back to itself. It could go to the 3 choose 8. And then it could also go to W2 choose 8. Oh, wait, am I going? No, I'm going in the right direction. Yes, right. So in principle, I can start to write this down. I just calculate what's the probability I get something new. Here are the different possibilities. I would start not with needing 8 cards. I would actually start with needing just 1. So start with W1 choose 8 and work up. So this is very similar to the M&M game, where we're trying to calculate what's the probability Cam and Kayla eat their last M&M at the same time. I can set up these recursive structures, and then I just build it up. What's the problem about doing this for the problem that we care about? Why might this be a problem for what we care about?
This approach?
Yeah.
A lot. It's a lot to calculate.
It's a lot to calculate. We're going to have to go all the way up. And so how painful, yes.
You might not be, the sound might not be recorded.
Oh, no.
The click to join audio.
Oh, yeah, good. Yes, that's the audio on the laptop.
Oh, yeah.
Good, no, but no, thank you for checking that. Yes. This is because I want to be able to shift to a programming language in a moment.
Okay.
And so, but yes. So the question is, how bad would it be to program something like this? Theoretically, this is trivial.
This will be very redundant because you'll be calculating like 5 choose 8 a lot of times, for example.
Right, which is not well, but what happens as we start to go up to 52 cards rather than just 8 cards? You're going to have many more levels.
It doesn't scale well.
But I mean, again, at each point, the difficulty is you could get up to 13 new cards that you were missing. So the number of possibilities. But again, if you can program efficiently, this shouldn't be that bad. Yeah. And so I don't know if anybody's ever written up this problem. And if nobody's ever written up this problem, I think this would be a really fun thing to write up. It's a natural question. How long do you have to wait? And then there's the difference between how long do you have to wait as an individual before you see everything versus how long does everyone at the table have to wait before they see everything. Sometimes applications like this, you can view it as, having, certain failures and whatnot. And how long do you have to wait before everything has failed at least once? All right, so what I want to do now is I want to toggle to the computer program. So let's see if I can do a screen share. Stop the share here. Is it sharing? Yes, okay, good. Okay, so now, hopefully you can help me program this well. Step out of the way. Okay. And so long as I've used the computer, I'm just trying to just minimize this damn thing. Hide video panel. There you go. Okay. All right. So I started writing the outlines of the program to just simulate this. And again, this is the 21st century. If your first thought when you get a lot of problems like this is pen and paper versus writing computer code, we need to talk. Computers are very easy to use. They can run millions of simulations. If you try to do this calculation by hand, I showed you a recursive way to do it, but if you try to do it by hand, it's going to be a disaster. So let's simulate it. All right, so I just started writing just the outlines of the program just to save a little bit of time. So I'll call the program deal still see all. So we'll keep going until we see all the cards. Num cards underscore means that's, and numdo are going to be parameters that I'm going to feed in. So num cards will be the number of cards in a suit. And so again, you always want to be clear as to what we're doing. So I probably should be clear. Num cards in a suit. Okay. And then we'll just do this numdo times. And so I'm going to have a array num deals, which just keeps track of how many times it took D deals for a person to see everything. Deck is going to just be a deck of cards. And so I'm going to just initialize it to be empty. And then I'm going to just fill it with the numbers from 1 to 4 times. So if it's 52 cards, the numbers will be 1 to 52. As an aside, if you've ever taken a probability class, almost surely you've been given problems like, what's the probability in a hand of 5 you have at least 2 queens and at least 2 kings? A really good way of doing a problem, just that problem and not a general problem, is queens are 1, kings are 10, everything else is 0. And then just sum your hand. If you have 22 points, you have 2 queens. If you have 23, 2 queens and 2 kings. If you have 23 points, you have 2 kings, 3 queens. If you have 32 points, you have 3 kings, 2 queens. And so rather than checking to see which queens do I have and whatnot, just make all the queens 1, all the kings 10. If I now change the problem and ask how many hands have a straight, then the deck you made does not work. So this is a problem that you really have to think about whenever you're coding. Do you want to write the code to solve the specific problem at hand, taking advantages of the symmetries of that particular problem? Or do you want to spend the time and write something that's more flexible in general that you can then use to solve other things? And so here, I'm going to just make the deck from 1 to 4 times the number of cards per suit. And so my main loop is I'm going to go n goes from 1 to number of due in steps of 1. And then just each time I'm going to keep going until somebody sees everything. I could initialize it so that the first person is just dealt all the spades. I'm not going to bother doing that, but you could easily do something like that. So num deals is going to keep track of how many deals have happened. Have all is going to just be a quick check to let me know, has the person seen everything? And I'm only going to do is one person seeing everything. So again, if anybody sees anything that I'm doing wrong, if anybody sees a better way of doing things, let me know. And I'm going to just do it with a while loop. So part of this is to show you that you don't need high-level programming to write code to do some simple stuff like this. How many of you have ever seen the strategy, and I think we talked about this briefly, double plus one for roulette? So when I was young, my dad wrote some very basic code, and it might actually have been in BASIC, to simulate double plus one, and just how quickly, and he was shocked, and I was shocked watching with him, how quickly you go bankrupt. It's really valuable to be able to write stuff like this to simulate. So this is what I'm going to do. While have all equals 0, I'm going to take a hand, which is going to do a random sample from deck and num cards. So because I have 4 suits and 4 players, if there's 13 cards in a suit, each player, every hand gets 13 cards. So I'm just going to randomly choose 13 cards from the deck, and that's my hand. This was just to print it out to just make sure it's actually doing it properly. It was. And so I'll just run the code right now just once. So all it's going to do is just print out. It shouldn't take this long. It must be just waking up. Just going to choose a random hand once. I'm now getting a little bit worried that it's taking this long to choose just one random hand.
You ever have the thing exiting the point having saying?
No, I said I have not written the code to do anything. I'm just waiting for class to do that.
Oh, I was just saying maybe the wild is, I don't know how this works, but sometimes the print doesn't go until.
Oh, it could be. Oh, wait a minute. I might have added the while loop after we. And it's not letting me. It's now crashed.
Do you have a terminal? Like, can you do Control X, Control C to hit the process?
I was hoping to avoid doing that. Interesting. It's not actually. So that should have ended it. So let's reboot it. All right, so I'm not going to print out the first hand right now until open recent. Okay. So let's start putting in the code. So this was just to print out a hand. So we're not going to need to print things out. So now we get a hand. What do we do? So I've defined seen to be 0. So that means initially we don't have anything. So I think that what we do now is we go through the hand, and every time we have a number in hand, we just make seen equal to 1. So for C, maybe for card equals 1, C less than equal to num cards, which is the length of hand, C plus plus. And then we'll say seen of hand C equals 1. If we've already seen a card, do we need to do this? No. Does it hurt us to do this? No. And again, I don't know enough about coding to know if this is a bad idea. How much time would it take to check to see if if we've already seen a card there? Is it better to just assign it to be 1? I don't know.
You know branches, predictions if you have an if statement, so you might not be saving that much time.
Right. So I think it's probably best to just make this equal to 1.
Are you updating Pebble at any time?
I'm sorry?
Are you updating Pebble at any time?
Nope, now we have to do that. So now how do we check to see if we've seen everything? Good. I think that's the fast way to do it. Take the sum. So if the sum of seen Wait a minute, I gotta be careful. Scene, we'll do maybe D. We'll do I. If scene I goes from 1 to, now we have to do the length. I think it's 4 times num cards. Right? So that's going to be the sum. If that sum equals what? Num cards? 4 times num cards. Then have all equals 1. And now we should increase, actually we should probably have done this initially. As soon as we create the hand, we should update num deals equals num deals plus 1, because we just dealt another hand. This creates a random hand. Okay. So is there anything else we need to do? So we deal a hand, we increase the number of deals by 1. We then make sure that any card we were dealt, we make sure we record that we've seen. We check and see if we've seen all the cards. If we have all is 1, and we'll now exit this loop. If not, we'll do the loop again. I'm going to just put in, based on what happened, if num deals equals 1000 times 4 times num cards. And what we're going to do is have all equals 1, and we'll print exiting waiting too long. And then end of exit if statement. So this way, we will not get stuck in the loop forever. And you should always put in some save. So I do like things like Mathematica. I know not everybody has a lot of experience programming. It has this in a different color. Why do you think the equal sign is in a different color?
It's an assignment instead of an equality check.
Right, and so I need to have a double equal sign. And so Mathematica was alerting me that you probably made a mistake. In a few years, it'll just automatically correct that and make a little log that you can't trust Miller with, logical tests. All right, so I think that now goes through, and now we want to do some stuff before we get to the end of the end loop. So now we go back and we see where we're saving the results. We were saving the results in num deals. How long it took. So now what we do is we want to increment that. So now num deals of, wait a minute. I can't use num deals twice. I'm using it both for the array and I'll call it current num deals. Because I'm saving the number of times it took 1 deal, 2 deal, 3 deal, 4 deal in an array called num deals. I can't use that as the local variable to keep track of how many was it this particular time. So now I'll say num deals of current num deals equals num deals of current num deals plus 1. I think I probably could have just done plus plus after that. Would have just incremented it by 1.
Sorry, what's your num deals array?
So num deals is, it's a list. I'm sorry, it's an array that keeps track of how many times did it take D deals before somebody saw every card. So numDeals records how many deals of length D were there before a given person saw everything. I'm estimating that do not need to go further than numCods times log numCods times 4. Actually, I'll
When
put
you
in.
say a deal of length, do you mean giving out, say, like 13 parts to use 13?
No. It's just every time I deal, I check and see, does somebody have all the cards? Let's say it took 13, not, let's say it took 17 deals before somebody saw everything. Then I would increase numDeals 17 by 1.
Okay, yeah, okay. Yeah, the figures. Okay.
Right. And looking at the prize problem, I don't think it's going to take as many as, the number of cards times the log of number of cards. That's if I'm treating each card as an individual prize. And since we're getting, 13 of them at the same time in the standard deck, it should be much faster. The first deal, you would get 13. The next deal, you would probably expect to get maybe 9 more. The next one after that, probably 6 more. And so, you're more than halfway there after just 3 deals. So, and then
What maximizes the weight? Like what kind of hand?
well, I mean, the worst thing is if you keep getting the same cards again and again, it could take infinitely long.
Yeah, I understand that, but I mean the expectation, like it's definitely somewhere in
Well, the expectation is I was using the trivial bound from what we did yesterday, where just treat each card as an individual prize and collect them one at a time. So don't care that I'm giving you 13 cards. Only look at the first card of the 13 that I'm dealing you. Is that something new? Forget that you're getting 13. Just look at the first card. That should be greatly overestimating how long it's going to take. So every time I deal you 13 new cards, I only look to see is the first card new.
I guess my question to be rephrased as if we don't have other players who have 52 cards, but in this case we get hands of 13. In another game we might be getting hands of 15.
Right.
Is there a fast way to see, like, is 15 better for the wait time or worse?
Well, I would say the more cards you have, the longer you're going to have to wait to get everything. I would.
Probably no, if you have like 52.
The more cards you
cards in the
deal,
deck.
the better.
But the deck will be bigger. If you have 15 cards in a suit versus 13 cards in a suit, even though you're getting more cards at a time, I would still expect it to take longer because you just need one card that's bad that's not being obtained. But again, that's something that we can easily try to explore both theoretically and numerically. For small values, I think we can do it theoretically without too much trouble. If any of you want to try to write the code to do this, to write down the recursion, it might not be too bad with using a bunch of indices and just have, we have a flow and just look at all the different things. So the question is, have I missed anything here? I think this is more than safe enough in terms of how far I have to go. I'll put the 4 here to just write in the right order. I don't think I have to go this far. But I'll bump it up a little bit. I'll bump it up to 8. I don't think I need to go that far. That should be more than safe. But for small values, maybe there could be some issues. So really bump it up. It's an array, I don't care. And now I go through, I create my deck, and then I do my while loop. Do we agree that this seems to be right? And then I just record, that now it took this many deals. All right, and so now I want to find what's the maximum number of deals. So I start off with 1, and then I just go through my list, and I see, is that entry greater than 0? And if it is, then I just make max equal to that. And so that will give me the largest number of deals observed. That'll be the worst case in the numerical exploration. And then D goes from 1 to max. I'm just going to multiply by 100 to make it 100%, and I'm going to divide by the number that we've done to just give me the percentages. Then I'm going to make a list. This is the stuff I just did at home. I make the list initially empty, and then I go through, and for each one, I put in what was the percent that it took exactly d times. And I don't go beyond max, and then I just print this out. So does this look good? Are we seeing any? Yes.
Are we using that try to hold the value?
The max is in our NumDo simulations. What was the longest number of deals we needed before somebody saw everything? And this just helps me when I'm printing things out to know I don't have to go beyond this point. So does this look good? So whenever you have anything like this, you always start running it with something really small. Exiting, waiting too long. So that does not seem good. Notice how sum is in blue? Capital S for sum, I think. I'm not quite sure about why it's in different colors, but let's. So let me see. Let's just print the list. Num deals list. All right, so it's saying there was one time when it took 45. Oh, is this? Oh, this might not be sharing right now, because when we close things down, we might have stopped the sharing. All right. So let me just. Sadly, I will post the code, but all right. So it looks like it stopped. All right. So here's the code. It stopped sharing for a moment. Okay. So it looks like it's saying there was one time when it took 45. Most of the time, it was much less. So around 10.11% of the time, it was 15 deals. We're not seeing anything below 8 deals. So there was one time when it was 8 deals. That doesn't seem unreasonable. What's the fastest it could possibly be? 4. I'm just not understanding how it's displaying things with the color it's doing here. And one of the things we can do is we can print average. I guess it's mean. So mean wait time is, and then what else should we want? What else would we want? Yeah, the variance. And then one thing you can do in Mathematica is if you put a weighting, no, not weighting, timing around something, it will tell you how long it takes to run. And then you can often get some sense of how quickly will things scale. Okay, why is it giving me such a horrible standard deviation?
What's the column?
Which comma? This one, this one?
In the standard deviation and in the mean.
The problem is we have pairs. And so it's giving us the mean and the standard deviation of both quantities. And so if you multiply by 1.0, it makes things numeric. So that's easy to do. We've got to be a little bit careful when we're trying to calculate means and standard deviations.
You want to like multiply.
Right, because we want it, because these are not. So the first mean is just going to be it's calculating the mean of the percentages. So this is actually not what we want. So I will just comment these out. So what we can do is we have the percentages. So we can calculate print mean equals, and then what we'll do is we'll do a sum. And then if we do num deals d, that's going to be the probability that it took d times. And then we multiply that by d. D goes from 1 to max. I think that should be that should print out, I believe, the mean. Does that look reasonable? I multiply the percent.
Well, the average of the sum, right?
Well, each one is now weighted by the probability it happens. So the mean is, oh, okay, the mean is 1,631 because these are, I multiplied by 100 for percentages. Mm-hmm. So all right, that's easy to fix. So we just divide by 100. And so this is saying if we took 13 cards in a deck, we expect to take around 16, 17 tries before you see everything. And to put things into context, harmonic number 52. So 52 times the 52nd harmonic number is 235. So if you do it one at a time, it should take you around 236 tries before you see everything. If you're getting things 13 at a time, it should be a lot faster. You can then try to plot and see how do things change. So for instance, if we try to do things with 15, we were seeing, I think it was around 16 and a half. So now with 15, it was 16.7. So it went up. It's not immediately clear that it should go up. It feels like it should because there's more cards to get, even though you're getting more cards at a given time. There's more things that you need to get. And if you're just missing 1 or 2 at the end, it's going to be percentage-wise, you're missing a much smaller part of all the cards. So it should take you longer to get that final one. So again, this is how you get research questions. If I increase the size of the deck, if I increase the number of cards in a suit, do you start getting a higher fraction of the total cards faster in the beginning, but then to get that final one takes longer? There's a lot of good questions you could ask. I'm not sure why the histogram is coming out like this. Oh, wait a minute. Oh, it's not a histogram that I want. I'm using the wrong plotting command. It's a list plot. That's why I was having this. This should look much better.
What was the histogram there?
It is making a histogram of the results. That's not what I'm saving the results as d comma how many times it took d tries. It should be a histogram. It should not be a histogram. It's set up to be a list plot. All right, what do you think would happen if we took a large deck of 100? What do you think? What do you think the shape would start to look like?
Yeah.
So do you think it's still going to stay right skewed?
Probably more right skewed.
I'm not going to do 2,000. I'll just do 20 at first to see. All right, not enough to really get any sense. So let's go up to 200. All right, so this should take about 10 times how long that one took. And so it doesn't look, I mean, it looks like the time is going up a little bit. Would you say like around 25 maybe for average? 20? Looks like it was saying 19.7 Um,
Yeah.
and so is that the largest one 44?
So the average is 23 now.
The average is 23. It still looks very prominently right skewed. Do you think this could become a Gaussian? So many things become Gaussian. I mean, it's not an unreasonable thing.
I'd be skeptical. I feel like just because of what it is, like you have a very defined lower bound.
So you have this hard wall. You're not gonna be able to do it in fewer than for 13 cards and 4. If it's 1,000 cards and fewer than that, Well, actually, no. It's always going to be 4. It's always going to be 4. The way we've got it. It's always going to be 4.
5, 6, 7 are also like
Right.
never gonna happen.
Right. And the more cards you have, the least likely it's going to be that. But that could be an argument that it becomes Gaussian. That as you get more and more cards, you're going to get so far away from that hard boundary of 4 that for small values, that boundary could be quite reasonable to prevent Gaussianity or anything like that. But once you have suits with 1,000 cards, the fact that you have to take at least 4 deals doesn't matter anymore.
You mean that's like a -17 score or something?
Something like that, yeah. It's just so unusual at this point that it's effectively, I have infinitely far I can go in that direction. But in situations like this, as you get more and more cards, it's to get that final card could take a long time, and there could be some more variance from that. And so you're looking at this, we went to a deck with 100 cards. That's a good sized deck.
It's good with a million card deck.
And so again, this is not a great code. So I'll go up to 1,000. And let's go down to just 20 simulations. And then the question is, can you write the code much better than this? This is why I'm really happy when I see CSV. Okay, so for it did 20 pretty quickly, and the mean was 32. And it was taking about 7 seconds. So to do 200, we're going to talk a little bit over a minute now.
The 32, so I don't know, like just intuitively seems so low. Like it barely rises as you increase.
Well, so this is a great question. So if we have the veterans visiting on Friday, we will do a military problem, probably the German tank problem. If not, how many of you have seen the birthday problem? How many people do you need to have in a room before you have? Do you know how this changes with the number of days in the year? How does it scale? So it's probably around 22. But how does it change if you have, say, everybody moved to Pluto? Right? You now have Plutonic friendships with years of 90,000 days. How many Plutonians do you expect to need? Okay, so it was around 33. That still looks skewed to me.
Yeah.
But notice how all of a sudden, we've got some interesting questions. I could easily see, I run research both in the small RU in person here, as well as the Polymath Junior program online. I can easily see creating research questions from this. This is one of the goals of a class like this. How do you come up with research questions? This came from, I was playing bridge with my family, and, my son had 6 spades. My daughter, she did not cheat. She had 6 spades as well, which would guarantee my son a horrible trump split. She passed, did not show excitement. My wife passed. I had no spades. I had a lot of points, and I was debating, should I gamble and just choose another suit? And my daughter's doing everything she could. She wants to say, pass, Dad, pass, pass, pass. I've got him. But she did not cheat. She stayed very calm, didn't give anything away. I debated and said, I'll pass. And then it was an absolute nightmare for my son, where he's got 6 spades on his left-hand side. So as he's playing, my daughter always plays after him. It was a disaster for him. Nothing he could do. And so this inspired us. We were talking about some strange distributions and whatnot, and just seeing cards, and it led to this question. And I will leave with another question that our family came up with. Sometimes it's not easy to get everybody to agree to do something as a family, so you sometimes have to give incentives. And so to get everybody to agree to play, it's like, well, okay, Kayla, if I get 15 points and you get 20 points guaranteed, aces 4, king 3, queen 2, jack 1, there's 40 points total. You and I will have 35 points. Can we play under those conditions? Is it possible for Cameron and his partner, you need to know some bridge, to win having only 5 out of 40 points? It is doable. It is not doable with 4, and the answer is the pigeonhole principle. So it's just always interesting to see where things come from. So I'm going to stop here. I will just quickly scroll back up for the coding, just so that, and I will put the code in the slides as well.
What did you say? Veterans coming by? What's that?
Let me just